The broadcast is now starting. All attendees are in listen-only mode.
Welcome to the FEKO webinar series for 2013. We would like to encourage you to post questions for the presenter in the area provided on the side of your screen. These questions will be answered at the end of the session. For further information on FEKO, please visit our website or contact your local distributor. You are also welcome to contact us via the email address that appears at the end of the presentation, webinars@feko.info. Mel van Rooyen, our Senior Support Engineer, will be presenting this webinar, CAD Fixing in FEKO. Over to you, Mel.
Thank you, Fiona. Okay, just an introduction. The first thing we want to do when we want to do EM simulation is we want to get a valid model. Now, faulty CAD is always a barrier to entry into the EM simulation environment. CAD problems can result in an inability to create a mesh at all, or we create a mesh but with discontinuities, or the mesh may be very inhomogeneous. Now, with inhomogeneous, I mean the ratio between the very smallest triangle and the very largest triangle. If this ratio is typically a few thousand, we go to the matrix could become singular or near singular, the method of moments matrix in FEKO, and that could cast some doubt on the accuracy of the results. It could also happen that we have extra solution time because we meshed elements that weren't necessary in the first place. We had a larger mesh or more mesh elements than necessary. And we can also end up with inaccurate or wrong results if our model is not really representative of the actual model because of the CAD problems. Now, quite often a CAD model is created by a mechanical engineer and it is not suitable for EM simulation. For example, there will be much detail in the model. For example, there could be rivets and screws and many small details that we don't really need in EM simulation. Now, it's always best to reduce the CAD model for EM simulation in the original tool the model was created in. But that is not always possible, and many of our customers have requested that we add basic CAD fixing tools native to FEKO because they want to work in one tool. So in Suite 6.3, we added the CAD Fixing Tools groups on the Transform tab, the Repair group, and the Rebuild group. So in the Repair group, you'll see on the Transform tab, the Repair group, we have the Repair Part tool, the Simplify Part Representation tool, the Repair Edges tool, the Repair and Sew Faces tool, Remove Small Features, and the Fill Hole tool. Now, for the best results, you should apply the tools directly after importing the model. And note, these tools only operate on primitive parts. So if you have, let's say, something simple, there was a horn antenna and you made the length of the horn antenna using a variable L, and you assigned some value to this variable, and you use that variable for the length of the horn, then you will lose that parameter when you use the CAD fixing tools on that horn antenna. So the tools only apply to non-parametric geometry. Now I'll demo a few examples to show you how these tools work. So then we go to CADFEKO to look at the examples. The first one we'll look at on the Transform tab is the Repair Part tool. Now this CAD fixing tool yields a body in an attempt to create a valid solid. It will attempt to remove several problems such as self-intersecting geometry, missing or misplaced vertices, non-G1 geometry, etc. Now this model is actually a model of a human ear, and it really does not look like this at this point in time because of the many problems. If we look in the model tree, we see several red exclamation marks, these red triangles, and if we hover over them, we see part contains many faults. So let's apply the repair part tool. Now, most of these tools also have advanced options, but we don't have time to get into the advanced options now. I suggest you look in the manual, but for now, I'll just use the simple method and then click OK. Now this will take a few seconds, so while that is busy, I'm going to move on to a next example, also on the repair part, and that is this bottle model. So this model is a model of a bottle, and it should be a solid, but there are some problems in it. If we click on the model, we see the red exclamation mark, and if we go in the detail tree, we see further problems. If we hover over the faces, we see some further tooltips. Vertex does not lie on edges curved, and so forth. Now, let's focus on phase 19. There it is. If we look at phase 19, it's indicated as a face in the detail tree, but in the 3D view, we can actually look right through it. So this face has got many problems. So let's apply the repair part tool. This will just take a second or two. Okay, we see in the message window, 2 faults remain, but several of those red triangles have disappeared, and also that face is now a proper face. Now it's still showing in the message window 2 other problems, for example face 145. So if we click there, we can find them, and to view them we can go to display options and then use opacity 0%, and that will highlight this face for us. And also face 146 is up there. So these are 2 very small sliver faces. Now for EM simulation, for most practical frequencies, these faces are so small they are electromagnetically insignificant. So one thing we can do, we can just remove these faces. So I'm going to delete them. But there's one downside to this. We were trying to model a solid, and a valid solid part should always have a region indicated in the detail tree. When a region is shown here in the detail tree, it means all the faces bounding that region or that volume are continuous, and that in all likelihood we can make a continuous mesh out of that part. So right now that is not possible. So let's look at another tool, the Repair and Sew Faces tool. The Repair and Sew Faces tool tries to sew different faces into a solid or sheet part. So I'm going to use that tool and specify a tolerance of 1e minus 5, which is about the size of those sliver faces. And then click OK. Okay, and just one thing here. I'd said to apply the tool to faulty parts. Of course, it's not showing any faults, but we're still trying to generate a solid, so I'm going to just change it to entire model. So the original model was a valid model, but it wasn't a valid solid. So now we have sewn the faces together, and we see, aha, in the detail tree, a region appears. Now, where it's also important to have a valid solid is, for example, when you use the MLFMM method. If you've used the method many times before, you may have noticed that sometimes it's difficult to get convergence for the solution. And one thing that we always suggest at support, and you'll also see in the Help Center, there's an article on the convergence of the FMM, how to improve it. If you read there in the Help Center or if you contact support, we will tell you to apply the combined field integral equation, or the CFIE, to your model, which will improve convergence. And you can only do that when you have a valid solid. So in this case, we will be able to use the MLFMM with that improved method for convergence. Okay, now just to check the meshing, because remember we deleted those faces, just to really check if if the sew operation was successful. And just go back to 100%. Let's create a mesh just to double check. So let's go to mesh, then create mesh. There we go. Any value, it's not really important now. So what we want to check now is if the mesh is continuous. We want the triangle edges to line up perfectly. We're going to look at specifically those two areas where we deleted those two sliver faces. Okay, and to view the mesh, we go to Display Options, Simulation Mesh. We zoom in, you see, aha, a nice, beautiful mesh there. The one sliver face was down here, and the other one was up here. So that's great. The mesh looks nice and continuous, not very inhomogeneous. That is a good mesh. Let's go back to the ear model and see what happened there. See, great. We have fully recovered the faulty geometry of that ear model using the repair part tool. Now let's move on to the next one, the simplify part representation tool. Let me load the next model. The simplify part representation tool simplifies a curve or a surface by attempting to simplify the curve or surface into an analytic curve or surface. What we have here is a model of two coaxial cables. No parameters have been set yet, so it just looks metallic. If we go to the model tree again, you see some red exclamation marks. Part contains geometry faults. If we go into the detail tree, for example, loops inconsistent. So we have some problems there. Also, phase 3, topology's geometry is not G1 continuous. Okay, so let's select simplify part representation. Okay, so in the message window, We see some feedback, number of underlying geometries simplified 2, but there are still some problems remaining. We see in the model tree, 2 of those 4 parts no longer have problems, but the other 2 still have some problems. Okay, now to fix those other 2 parts, we use a tool that's been available. Let me just see, just a second. Lost my place here. Yes, we're going to use the repair and sew faces tool for the other two parts. So we go to repair and sew faces. And what we have remaining is 2 faulty parts. So we select the faulty parts. Okay, we see the red exclamation marks have disappeared. But what is still remaining, if we want to, there are some redundant edges on the coax. Some redundant edges, that edge there and that edge there. And we can remove that with a tool that we've had for a while. That is the Simplify tool. Now if you click this tool, okay, this tool simplifies selected geometry by removing non-essential edges, faces and wires. So we click that tool and specifically we will use remove edges on metal surfaces. Remove edges on metal surfaces is checked. And we see those edges are no longer there. We also see in the detail, in the message window, some feedback there on what has occurred. Now let's look at a more extreme example. Okay, what we have here is 4 faces. They are completely disjointed. So again, this is an extreme example. And we want to generate a continuous mesh across these 4 faces. This is quite a challenge. We've got those big gaps between them. Also, again, there are problems, not just with the fact that there is a gap, but also the actual definition of the faces. Vertex does not line, edges curve, for example. So let's click Repair and Sew Faces. Now if we click OK, we see the red exclamation marks have disappeared, but we still have these gaps. And if we were to make a mesh, let's create a quick mesh. Custom mesh. We still see the gaps, so there will be no continuous current flow between these 4 faces. We want that. So let's undo the mesh. Just look at the model view and then go back to that tool. Now let's make that tolerance a bit bigger, actually a lot bigger. Again, this is an extreme example just to really demonstrate the tool. I'm going to do it on the entire model because they're no longer faulty parts, so it's on the entire model. Now it looks like this. Now because of the big gaps that were there, some display artifacts remain on the geometry, but the real thing is, how does the mesh look? So let's create another mesh. And then we look at only the mesh, not the model. So we don't look at the CAD, we only look at the mesh. Now if we zoom in, we see, great, the triangle edges line up perfectly. So if this plate was illuminated with a plane wave, there will be continuous current flow all over the place. Or if you placed an antenna on this, it will act as a fully continuous ground plane. Okay, but now a little bit more about the Remove Small Features tool. So let me go to that model. The Remove Small Features tool attempts to remove small features such as edges, faces, spikes, and gashes. So if we zoom in on this model, we see two small faces there, and also there's a gash here. And if we go up a bit further and zoom in, there's also a gash there. Now, as I mentioned in the beginning, the CAD Fixing Tools only operate on primitive parts. And right now, we don't have a primitive part. So we convert the model to a primitive by selecting the part and then clicking on Convert to Primitive. The tooltip states, reduces the complexity of a model component by ignoring its creation history and using the component as a base component. Okay, so now we have a primitive, and in the tree we have that little icon there. Now we can remove the small features. We go to remove small features, and the small feature size is the size of the gash and the face. We take that into account. Click OK. Now we see the two small faces have been removed. Again, some display artifacts remain, and we can test again by creating a mesh. So let's create the mesh. And then we view only the mesh, not the model. And we see, great, continuous mesh, the triangle edges, they line up. There are no small faces remaining, and also around here we had that gash, also a continuous mesh. Now onto the Fill Hole tool. The Fill Hole tool. Okay, so we've got several parts here that we want to demonstrate the Fill Hole tool for. The different options for the Fill Hole tool. This tool attempts to fill a hole based on the selected free edges surrounding that hole. Several options exist for how the hole can be fixed. We will demonstrate each one briefly on each part. Okay, so let's go to the first one. We want to fill the hole of this box here at the top. So we must select the edges around that hole. So we go to Tools, Selection Type, Edges, Tools, Selection Type, Edges. Select the edge. Now we could go on and select all the edges, but I want to show you a selection tool that was added to Suite 6.3 to make this easy for you. Go to Selection Tools and then select Edge Loop. Select Edge Loop. If you read the tooltip, if it's maybe small, the smallest loop containing this edge will be selected by this tool. So we click it and we see all 4 edges have been selected. And then we go to transform, fill hole. First one to show is the cornered face-to-face transition. This allows the hole to make a corner with the faces bounding the hole. Okay, so that hole is filled. We go on to the next part. Just ensure again we have select edges. Okay, that's active, right? We use that selection tool again. There's also a shortcut that I'll use. You'll see in the tooltip Q and C. So you select one edge and then Q and then C and then all the edges will be selected. That is the shortcut. So we go back to fill hole again. Now we ask for a smooth face-to-face transition. This allows a smooth transition between the bounding faces. So our hole is now filled like that. For the third part, I select one edge, Q and C to select all 4 edges. Now I'm going to remove the hole. Fill hole again, remove hole so it extends the bounding faces. And we end up with that. Right, onto the cuboidal parts. Select the first edge, QC, and then fill a hole. And we'll also remove this hole. And now there's no evidence that the hole even existed. Second part, QC, fill hole. And remove hole. Now that was the first one. Just go back. I'm going to do a cornered face-to-face transition. Cornered face-to-face transition. So then we can still see where the hole was. In this case, it's not really a corner because it's just a flat face. But we can still see where the hole was. Let's go to the first cylinder, see the behavior there. So we select the edge and we're going to use the cornered option there. We get that. For the second cylinder, let's see what we can do with a smooth face-to-face transition. We get that. For the third, more triangular shaped cylinder, cone shaped, we also do smooth face-to-face transition, and we get that. And lastly, for the fourth cylinder, we're going to remove the hole. Remove the hole. We get that sharp tip cone. Okay, and another example for the fill hole tool. Let's go to this model. Select one edge, QC, and then go to transform, fill hole. I'm going to do a smooth transition. For the second one, Q and C, and what is interesting, we select, CADFEKO selected this loop as the smallest loop. So this selection tool will always select the smallest loop. So I could fill this loop, or I can undo and I can just manually select, for example, the larger loop and fill that as well. And the same for the rest. And also this very funny shaped wire here, Q and C, full hole. There we go. Okay, some closing remarks. The tools that we have demonstrated only act on primitive or collapsed parts. That's very important. So your model will be non-parametric. This is because the tools act on the underlying geometry directly, not on the parameterized model. It is best applied directly after importing a model. You can also apply the tools at any time as long as you collapse your part to a primitive. So you can create your model with parameters if you want to, if it's easier for you to do it like that. But remember, if there are some problems in the model and you have to fix them with these tools, you're going to have to change it to a primitive model. Now there's no exact recipe to CAD fixing. In a number of cases, it is necessary to apply a number of the tools in succession, and sometimes you're going to have to go through a trial and error process to fix your model. And in terms of the tolerances, it is best to use the smallest tolerance possible, or not at all if the option allows. Now we encourage you to use these tools, to play around with them, and please contact us if you have suggestions on how they can be improved, or if the tool doesn't quite work as intuitively as you thought. You're welcome to contact us. I want to thank you for your time, for listening to us. Again, please play around with the tools and please provide feedback to us.